Guys, we'll start. Hi everyone. My name is Ayush. I am marketing specialist at Sendra. With me, I have Manvinder Singh, R&D engineer Sendra, as the speaker of this webinar. And I will request Manvinder to start the webinar. Manvinder, please go ahead, unmute and go ahead.
Yeah, Ayush, thanks. Am I audible? All right, let's get started. Hi, everyone. Warm greetings to you all. I'm really excited to be on the stage again, and this time conduct this webinar on a really exciting yet important topic, and that is deploying reliable LoRaWAN network. Well, your host today is Manvinder Singh. I am an R&D engineer at Sendra. Sendra, we are a pan-India LoRaWAN network operator and an end-to-end solutions provider globally. So we have been around for a while. It's almost 7 years now. We are part of the LoRa line since its founding days. And one thing that we have realized is that LoRaWAN has limitless potential. And it does have the ability to change the world, and it is already. Provided, and that's really important here, provided that it's implemented the right way. And we were given this wonderful opportunity to pioneer the onset of LoRaWAN in this diversifically rich country, India. And we have met an enthusiastic set of customers, vendors, and partners. And through their projects, we have learned a lot. From some small scale POCs of a few dozen devices in a gateway to over a few tens of thousand devices running seamlessly on our network today. I must confess that it hasn't been since the day one. Uh, we have stumbled upon, we have learned from our mistakes, and what we have eventually landed up with is a very exhaustive list of best practices and implementation methods that are to be mandatorily followed by us or by any other network operator, system integrator, solution provider, whatever you may call yourself, to be mandatorily followed in order to achieve the desirable seamless network performance. And so is the agenda for the day. We'll start with the best practices focused around devices. What I mean by that is something that I'm going to talk about shortly. And then we'll move forward to a product introduction of Netsi, a tool that will seamlessly enable you to do everything that we are talking about in the best practices. So without any further ado, I'll get started. And like any LoRaWAN slide, I'm bound to have network architecture slide because it tells a lot. And just focus and bear with me for a moment here and try to understand what a network architecture in LoRaWAN looks like. It composes of four components. The first one being the end devices. Then there are gateways. We have the network server and the application server. These are the four main components of a LoRaWAN network architecture. Now, if you look at network server and application server, they're basically one, like they're one each, they're not many. On the other hand, LoRaWAN gateways are in a order of a few dozens in a single network. But if you look at the devices, they are in the order of a few millions. So if you look at the velocity or the density, this component, end devices, has the maximum impact, which sends a signal, and that is that if these devices are not top-notch, if they are not of carrier-grade quality, and the right devices are chosen for the network, what will happen is that no matter how good the gateways are placed, no matter how well the network planning is done, how intelligent your network server is, and how fancy your application server looks like, everything will start to fall apart if the end devices are not carrier grade quality. So it's important to have the right best practices instilled in your end devices so that everything runs seamlessly. And in this webinar, we are going to talk about some abstract level end devices best practices. And in order to do that, we have to dissect a device. And by dissection, I mean talk about what all is present in a LoRaWAN end device. So if you look at a LoRaWAN end device, it has three sections. The first one being the sensor. Sensor is the one that is physically interacting with the external world, converting physical phenomena into bytes, information bytes that are then passed on to the microcontroller. This is the brain of the entire system. The microcontroller then is connected to the radio and has a to and fro communication with it in transmission and reception. The radio is then connected to the antenna through its power amplifier, and this entire circuitry is called the RF circuitry. So there are three major sections: sensor, microcontroller, and radio. That's it. So what we're going to do in this webinar is to talk about all the best practices on an abstract layer of these three sections, starting with sensor, and sensor being the most important for the application side of the things. So our part one is going to be around sensor characteristics. And the first characteristic that you have to really look at is the sensing requirement. What I mean by that is that, and I think it looks so intuitive and so rudimentary to understand what is it that you're trying to sense. And a lot of people actually overlook this. They think that they know what they're trying to sense. They buy the sensors, they buy the end devices with those sensors, thinking that they're buying the right thing. But eventually what they'll end up with is a sensor which is actually not meeting the customer requirements. And we have seen people not thinking through, not brainstorming enough at this stage, leading to disastrous as the project scale. And I'll give you an example here. For example, you want to measure how much water is being flown in a household, right? So this is a typical LoRaWAN use case in utility where smart water meters are deployed all across the society, wherein we are basically trying to measure the flow of water within a household. And we do that with the traditional mechanical meters with a smart unit on it. And everything runs seamlessly when you're actually measuring water flow in a household using a mechanical water meter. Now, what you try to do is using similarity, you think that even if this water is not the water that is being flown in the households, it's a sewage treatment plant water, maybe a water which is a little too muddy, has sediments in it, and it's a little greasy. You think that the same STP water, sewage treatment plant water, can also be measured using these mechanical water meters. And that's where we make a mistake. When we start measuring STP water meters using mechanical metering make, what happens is that it starts to corrode the make itself. Not just that you're going to get very poor accuracy, the make itself will destroy itself in about a few months or weeks. That is really suboptimal. So what you then start to do is to look out for alternatives. The alternatives being an ultrasound, which can potentially be used for STP, I would say, but will have a really poor accuracy, which you basically don't want, because that way you will not be able to ensure customer delight. You'll be able to solve the purpose, the product won't corrode, but eventually you'll not get the reliability and accuracy that you want. So what is the final thing that you have to go with when you're actually talking about STP or sewage treatment plants? You want electromagnetic sensors. So these are again part of water meter space. And typically vendors that are providing smart water meters will have mechanical, ultrasound, and electromagnetic. But it's you who has to very precisely identify what is that you're trying to measure, and then choose the right thing in accordance to your requirement. It's not something that vendor will come up to you and say, okay, this is what you want, we'll get you that. You have to convey and ask the right questions to your vendor in order to get what you want, unless otherwise you want to end up having something that is totally disastrous. Well, you initially had, say, 1,000 of vendors to choose from. Once you lay out your exact precise requirements, say electromagnetic water meters, then you'll be down to from about 1,000 vendors to just 100 vendors immediately, once you precisely identify your sensing requirement. And that is really important. What is more important than that is what we have been talking about, and that is accuracy. So you have to precisely identify your accuracy requirement as well. For example, you're monitoring temperature. While you're monitoring temperature, are you okay with the actual room temperature being 25 degrees Celsius and what your sensor reports is 27 degrees Celsius? Are you okay with that? You have to ask that question to yourself, to your client. Can you afford inaccuracy? Well, regardless of what your answer is, yes or no, I would say that you have to learn to live with the inaccuracy, I would say, because no sensor in this world is immune to accuracy limitations. Every sensor will have its own inaccuracy limits, and you have to know them before you purchase them. And the typical way of representing a sensor accuracy is being done by least count. Least count is nothing but the closest number that you will get. So for example, you'll be reported 26 degrees Celsius. And if your least count is 1 degree Celsius, then that means is that the next sensor reading that it will give is going to be 25 degrees Celsius, nothing in between. So least count is basically 1 degree Celsius in this case, stating that there will be a 1 degree difference in the next reading that you will get out of the sensor. Everything in between will be just lost. So you'll have to know from your vendor what is the least count your sensor is delivering, and then have a conversation with your client, understand that, okay, we are buying you this sensor, this end device, which has this least count. Are you okay with that? If not, then you would want to go with some other sensor which has a different least count. For example, this one, wherein the least count is 0.25. Now, in this kind of a sensor, you will not just get 25, 26, 27, but everything between that, from 25 to 25.25, 25.50, and so on and so forth. So it's important that you understand your precision requirement, accuracy requirement by having to and fro conversation with your client, and then freeze the accuracy statements. Now, typically, the way that the accuracies are defined, they are not defined in absolute terms, they are defined in percentage. By that, I mean is, for example, you have 25 degrees Celsius, then sensor can report anything between 23 to 27 degrees Celsius, and that way the inaccuracy become plus minus 8%. So this is how the inaccuracy or accuracy limitations of the sensors are defined in percentages. So you definitely want to go with sensors that have less percentage inaccuracy. You definitely don't want to go with the ones that are super high, and that comes with a trade-off, because if you are going with low inaccuracy sensors, that means that you're going to pay more money to the vendors in order to get a better accuracy. That's it with accuracy. What's next? It's the range. Now you have to know your environment extremes, right? We understood what our sensing requirements are. We understood what our accuracy limitations are. Then we have to understand your environment extreme. Where is that you are going to place your device? And what are the worst case scenarios? For example, if I'm using a temperature sensor, my temperature sensors can be put in an ideal situation 25 degrees Celsius, and in worst and best cases from minus 10 degrees Celsius to plus 60 degrees Celsius. That's a wide range. You have to know, however, that your sensor reports this wide range, because sensors are actually designed to serve a certain range, not everything from minus infinity degrees Celsius to plus infinity degrees Celsius. It is bound to work in a certain range, and you have to know that. If you don't, then you'll eventually land up doing something which is suboptimal for your client. And I'll give you an example. And we had a client which came up to us saying that they have bought a humidity sensor and they're not able to deliver the right information to their client. And what happened in that case, I'll come to that, but I'll quickly just bring everybody on the table to help understand what humidity is and how it's measured. It's basically measured in SI unit called RH, that is relative humidity, that's represented as percentage RH. And a comfortable RH is 30 to 60%. What RH is essentially, so for example, you have 25 degrees Celsius ambient environment. At 25 degrees Celsius, the maximum holding capacity of the air is 24 millibars. So that is the amount of water vapors that air can hold. That is 100% humidity capacity of your air itself. Now, if in that kind of an environment at 25 degrees Celsius, you actually are having 12.5 millibars of humidity, then that humidity will be represented as 50%, because it's 50% of its maximum holding capacity. And at different temperatures, you will see different maximum humid capacity of the air. And that's basically shown in the graph on the right. So long story short, the SI unit is RH and it's percentage relative humidity. So now what our customer wanted to do is to measure humidity in potato cold storage. So they were basically taking care of the potato in a cold storage environment. And in this environment, the temperature was varying from minus 2 degrees Celsius to plus 4 degrees Celsius. That's relatively low. And in this environment, they are supposed to get 90 to 95% RH humidity levels in a curating stage of the potato. So if you're having potato in a curating stage, that means they're growing and you want to keep them preserved, you would want to have 90 to 95% RH in the environment. That is important for them to be, progressive in nature, not deteriorate. Now, if this is your humidity requirement, then you don't want that your humidity in the environment goes below 90 or plus 95. Otherwise, the system will start to fall apart or the potatoes will degrade. So you need to have a sensor that gives you that level of range. But if you're buying a sensor that is basically having a range from 10 to 60% RH, then you can't really measure 90 to 95%. And if you can't do that, that sensor is of no use to you in this environment. So this is how intuitive it is. You have to know what your sensor range is and what your environment range is, what is that you're expecting, and keep them in resonation, or else you'll not be able to make use of that sensor at all. Speaking of which, you also have to take care of the operating temperature. And that's something only you know, or maybe your customer know. You have to understand what will be the typical operating temperature of my environment. Because guys, we are talking about semiconductors here, and semiconductors change their behavior based on the temperature that they're operating on. So what would happen essentially is that if you have a really high temperature, the semiconductor will change its behavior, and what will start to happen is that your percentage accuracy will decrease or increase, whatever may be the case. So it's not constant. The percentage accuracy, it's itself not constant over an entire temperature. It is varying, and a typical variation looks like this. A percentage accuracy at plus 25 degrees Celsius is very small. It's very ideal. It's just 1%. But if you are putting the device in plus 60 degrees Celsius, the percentage accuracy changes. And that is something that you have to keep in mind. Because, for example, we have a customer that was actually making use of CO2 sensor in a greenhouse plant. So why CO2? Because CO2 is something that is trapped within a greenhouse plant to enable photosynthesis process. So you actually want to measure what percentage, what parts per million CO2 is present in the greenhouse, and that way open and close the valve to make sure that you have the right amount of CO2 to enable the photosynthesis process optimally. So they wanted to measure CO2. And this particular setting is in an open environment. And in this environment, you'll see different seasons. So this CO2 sensor will see many seasons. That means that it will see temperatures varying all the way from 25 degrees Celsius to 50 degrees Celsius, or even a wider range. What that is telling you is that in different operating temperatures at different seasons, you would see different percentage inaccuracies. So at 0 degrees Celsius, so 25 degrees Celsius, you'll just be able to see 10 plus minus 10 parts per million. That's fine. You are okay to, and you can learn to live with it. And that's absolutely fine for your use case. But when the temperature outside 0 degrees Celsius, the inaccuracy is plus minus 30 parts per million. But you can't live with that inaccuracy because that will destroy the field altogether. That will destroy all the crops altogether. So you have to understand and make sure that you have least inaccuracy deviations with operating temperature, and that would only come with sensors that are of top quality. That also means that they will be expensive. Or you have to offset these variations or either on the sensor or on the application. You have to understand first, make a note of them, and try to see how you can offset them and understand whether or not you need to buy another sensor. So many things: sensing requirement, range, accuracy requirement, then operating temperature. What's more? Zero drift. And that's something which we wanted to put together in our slide because we have experienced that, because we've been around for a while. We have seen sensors that are running over a few years now. And what happens with sensors, and that again is because they're semiconductor, is that they have a baseline drift. What that means is that there is a gradual deviation in what the sensor is reporting. For example, the real temperature is 27 degrees Celsius right now. The reporting temperature by the sensor, when it is actually very fresh, just out of the box, it's absolutely precise. It's 27 degrees Celsius. What's reported is also 27 degrees Celsius. But what happens 2 years down the line is that the sensor starts to experience a zero drift. That means that the real temperature is 27 degrees Celsius, but what's reported by the sensor is 30 degrees Celsius. So you'd see a drift. So that's what is called as a zero drift. And you want to make sure that there is a minimal zero drift in your sensors. And that again will come with a cost. But that is something that you have to ask to your vendors. Ask them that at what stage will I be able to see these zero drifts, and can I avoid them altogether? And can I get a sensor that has minimalistic zero drift? And that is also a question that you have to ask yourself. Let's say the zero drift comes after 5 years and the project itself is supposed to run for 4 years, then any numbers on zero drift really won't matter. But you have to ask these questions straight away to your vendors and then get back the right requirements, brainstorm it with your customer and understand what is that they want when it comes to zero drift. Last but not the least, a really important one, and that is sampling rate. So you would see sensors sensing information at a certain rate. So sensors cannot be up every second or every millisecond or every microsecond. They were only up at a certain interval. They sense it, go back to sleep, sense it, go back to sleep. Now, at what rate the sensor is actually sensing the information is really crucial, because what might happen is that your information itself is coming very rapidly. It has a very high sampling rate, but your sensor is not having the optimal sampling rate to sense that information. What you'll eventually land up with is loss of information. So if the sampling rate of your output is more than the sampling rate of your system input, then basically you will start to see loss of readings. So you want to make sure that your sampling rate or time gap between each reading is in accordance to the output. What is going on, what is the information that you're trying to capture. So it's important to understand the information and also understand what your sensor can do when it is about sampling that information, and make sure that they're in accordance. Otherwise, you start to see loss of packets. I think by now, after understanding so many things around the sensors, we started with a few thousand vendors, right? There's so many vendors, the ecosystem has grown so much. With just one sensing requirement, we were able to boil down to say 100 vendors. Then asking more and more questions, some of them may not have the right answers. Some of them would back off saying that we can't deliver what you're asking for. And then eventually you land up with just say 25 vendors to choose from. So that's how you filter out the vendors based on what your requirements are around sensor. Okay, so basically that completes our part one, sensor specifications. Now, if you have any questions, what you can do is to just quickly write them down in the chat box and then we'll take it up later. But we are not done yet, because we have just discussed first part of the three parts, and we are going to talk about the next thing, and that is firmware. We saw that we had sensor, we had radio, we have microcontroller. In the second section, we are going to talk about the firmware side of things. And the first one being the uplink reporting interval, the uplink reporting pattern. And we spoke about sensor sampling rate, right? How frequently you are getting the information. Now, the sensor might sense information every 500 milliseconds. That doesn't mean that you are going to transmit wirelessly that information every 500 milliseconds. You just can't do that, because that's just practically impossible due to duty cycle restriction and time on air of the packets. So what you want is you need to have a very precise requirement of how quickly you want the actual physical environment reading to be reflected on your application server. And that is what is being decided by the uplink reporting pattern. So you'd have to ask yourself that what is your uplink reporting pattern requirement? Is it periodic in nature or is it event-based? For example, you would want to report the temperature every 6 hours. That means the new reading will only come after every 6 hours. Whenever the sensor will wake up after 6 hours, it will sense the temperature and then send that on an uplink. Or you want something else, that is that only when a temperature raises a certain level, the alert should be triggered, and then that's basically an event-based uplink, and that's going to be random in nature. And I want to emphasize at this point for everybody in the webinar today to very strictly understand what is that your requirements are, and try to see which out of these suit your use case the best. And also keep in mind that whatever you choose should lead to as less uplinks as possible, right? So if, for example, a good example of a periodic uplink situation is utility space. These are smart water meters. What you essentially want from these water meters is that every day or every week, you want periodically how much water is being consumed. That's basically a good example of a periodic uplink reporting pattern situation. On the other hand, let's suppose you have a panic button situation. Who would want a periodic uplinks from them? You want event-based uplink. Only when the button is triggered, whenever there is a panic situation, you want a uplink based on an event. That is basically event-based uplink. These are some really good examples of individual settings. But you have to ask yourself, can I optimize my system to have as low uplinks as possible by either going with periodic or going with event-based uplinks or having a mix of two? The aim should be to get information, and information is only by its definition newness. If you're not transmitting which is really new, something which is actually information, you're just redundantly sending information and congesting the network, and nobody wants that. If you really want to scale, and if we want LoRaWAN to scale, we have to be very cognizant about which uplink reporting pattern that we go ahead with. Then comes downlink, right? We saw that we had, so for example, a temperature monitoring use case. We are sensing information every 6 hours, sending temperature information every 6 hours, and everything is working fine. Now the customer says that we don't want periodic uplinks anymore. What we want is that the device should only send an uplink when the temperature is reaching a certain level or above. In that case, one thing that you can definitely do is to go to each sensor, flash the firmware, and make everything from a periodic way to a event-based way. That's one way. But imagine doing that for 1,000 of devices. You just can't do that. That's practically impossible, right? So what you need in that case is something kind of an instruction to the device to change its settings. It's to change its firmware settings, and that can be achieved with downlinks. So you have to understand what your downlink requirements are, and if none of you know what downlinks are, typically the information is being triggered by the end devices. So it's the end device when they initiate information exchange. Everything that goes from end device to the gateway to the network server and application server, that is what we call as northbound streaming. Everything is northbound, and that's what we call as uplink. But there are times when the application server has to transmit information back to the end device. In such a case, this is basically what we call as southbound streaming, and that is what downlink is all about. It's when the application server is when it initiates the message. This is what we call as the downlink. But you might ask, do you really need downlinks? You understand what downlinks are. Now you might ask that you really need downlinks. I mean, again, whatever your answer is, you actually need downlinks because you might not be able to appreciate the importance of having downlinks in your devices when you're testing things in the lab, when you have few devices, everything is just in the POC stage. You might see no importance of having downlink feature set on the devices. But as you scale up, as you solve problems of your client, and you basically are trying to achieve massive IoT with LoRaWAN, you will definitely realize the importance of having downlinks and downlink features within your firmware. And where will that come from is these. Downlinks will be able to help you modify your packet structure. They'll enable you to send some instructions command. It will also be used to change some network layer settings, and also at times, and that is not so common, but do firmware upgrades. So you have to make sure that whatever device, whatever vendor you're choosing, they're actually supporting downlink feature set. If they're not, they're actually not good vendors for you. For example, if you have this device and you're trying to modify its packet structure, initially the device was actually placed in a setting where the temperature was supposed to be monitored. In such a setting, the device was working fine, everything was seamless. But then you thought of placing it all together in a different setting where you also want to measure humidity, right? So you want to change the packet structure of your device. So how would you do that? You would send a downlink from the application server routed to the network server to the gateway to the device, and then the device will understand, oh, the requirements have changed. I have to change my packet structure. And once the device receives that downlink, it will no longer just send temperature, but will also send temperature plus humidity. So downlinks can be very effective when you want to modify the packet structure. Where else can they be used? They can be used to send instruction set. For example, earlier your device is sending uplinks every 6 hours. Now you've changed its settings from a temperature to a temperature plus humidity requirement. But what you also want is to save battery. It's almost 2 years, and your client says that we don't want information that frequently. We are done with having 6 hours information every now and then. We just want information every 12 hours and just want to save battery because we want to save OPEX. In such a case, you want to have a downlink feature set. You want to have downlink to be sent to the devices so that they can change their uplink periodicity. So these are the instructions that you want to change settings on your devices so that they do what you're expecting them to do, right? Third is network settings. So these are MAC layer downlink settings that you would want to go ahead with. For example, you want to change the channel plan of the devices or the data rate. So these are MAC layer downlinks. These are supposed to be taken care of between the network server and the device, but that's where also downlinks are used. Then there's something called firmware update over there, FOTA. That's also where downlinks can be really beneficial. So you have to make sure that your devices are supporting downlink. That downlink can be used either in modifying the packet structure, changing the instruction set, enabling network layer settings, or upgrading the firmware altogether. Now, I'll give you a tip here that's really important. If you really want to understand whether this device is for you or not, so let's say you're done with a list of 10 devices to choose from, and you want to choose the best of the best, look at the device or look at the vendor that has a really exhaustive list of downlink feature set, because those are the vendors that are there for a while. They have seen multiple massive deployments, have understood what are the client requirements are at scale. And they have made their firmware such that everything is basically configurable, all the way from how frequently the uplinks are reported, what kind of information needs to be transferred, if you want to change the modes, whatever it may be, the exhaustiveness of the downlink features will define the quality of sensor. And I have one with me from Tectelic. These are devices that have a really rich set of downlink features, and we have a very close tie-up with Tectelic, purchasing their devices for a while, and they run seamlessly, and clients are really happy getting those devices over the devices that are not from Tectelic, and that is because everything is essentially customizable. Now, you might not need customization at day zero, but maybe 2 months down the line, your requirements change or your clients want something more. Things are off the shelf when you're using the right vendors, when you have the right support on the firmware and on the downlink. What else? We understand that downlinks are important. Yes, they are. What is also important is what is your latency requirement? So do you want your instruction to be reflected on the devices immediately? Or are you okay with your instructions being read to the device maybe one day later? Based on what your latency requirements are, LoRaWAN has actually defined classes, right? So in order to understand latency requirement, you have to understand what device classes are, and we'll go through them in a quick 1 minute. So there are 3 device classes, class A, B, C. And over the period of time, the class A works as follows. It sends an uplink at its reporting interval, then open its ears for RX1 window time, then again open its ears for RX2 window time. And then it will go to sleep. It will not listen, it will not transmit, it will just go into a sleep mode for the next reporting interval that can be 6 hours, 7 hours, 10 hours, whatever it may be. And then it will again send an uplink, and then the same thing repeats, right? That is how class A devices work. Now, if you want to send a downlink to a class A device, you basically have a really limited slot. Only when the device will uplink, you can send a downlink in the RX1 or RX2 window. But if you have a class B device, that means you're sending an uplink. You will open your RX1, you'll open your RX2, you'll go to sleep for a moment, but then you'll again wake up to see if there is any downlink. You'll basically send beacons to your gateway for the gateway to know that you're waking up temporarily. And that's the time that the gateway can use to send the downlink to you. So it will keep up and sleep over and over again, send its uplink beacons every now and then send its actual uplink. So in a class B device, what you can essentially do is to send downlink intermittently anytime in between. So that is a lesser latent. But in a class C, which is continuous, and continuous, we mean RX1, RX2. After RX2, the class C devices are all open. What I mean by that you can send a downlink to a class C device immediately because they don't sleep. They don't sleep. They're keeping their ears open forever. and you can send downlinks immediately and they will be reflected on the devices. Now, what all of this is saying to us is that go ahead, use Class C devices because they won't give us any latency issues, right? So everyone must use Class C devices, but that's not the case because you also have to understand that when your devices are keeping ears open for a longer period of time, that means that they are consuming battery, right? They are consuming battery heavily as compared to devices that are sleeping more often, which essentially means that your Class C devices will not run on batteries. They can only run on AC powered source or solar panels. On the other hand, Class A devices can run on batteries and can run on batteries for years because they're sleeping most of the times. But on the other hand, you also have to understand that latency will be maximum in Class A devices. You'll have to wait for the next reporting interval to come to be having the gateway to send the downlink and seeing the reflections of your instructions. So based on that, and this is a quick summary of what we just discussed with such a long presentation slide, is that if you're using Class A device, you can send the downlink at the next reporting interval, which also means that your device sleeps more often. That's why low current consumption. For B, you can set it within the next few minutes as long as the beacons are there in the devices, but then current consumption will be medium. For Class C devices, current consumption will be high, but you can really quickly, immediately send your downlink messages. So when you're choosing vendor, you first clarify what your requirements are by discussing things with your customer, and then choosing vendors that are actually supporting all class devices. And that's what Tactilics do. All good vendors do. They have a wide variety of devices, and each device can be supporting class A, B, or C based on what your requirements are. So we have discussed sensors, we have discussed firmware also. There's one thing which is left, and that is radio. But I hope by now you're able to understand how would you filter out vendors based on the sensor characteristics and the firmware characteristics. Is radio really important? Because we've just talked about battery life, right? We saw that whatever our latency requirement are, whatever the class of the device is, based on the class of the devices, the battery life changes. What else actually changes battery life? It's actually the radio characteristic. And I think it will not be really hard to understand, but to realize that whatever is the set transmit power on your device, and that is part of the radio characteristics, whatever is the set transmit power on your device, it will impact the battery life, right? But it also means that a higher transmission power means a longer range. So if you're using 10 dBm transmit power on a device, it will range up to, let's say, 3000 meters in an urban environment. If you're using 14 dBm, then you would, of course, get a longer range, maybe 5000 meters. But one thing that we have to realize here is that we can't always use a higher transmit power. And the reason being is the higher the transmit power, of course, you get a longer range, but you have to trade off with the battery. How? It's really simple. Whenever a device is sending a message, it basically consumes some current out of the battery. So if you're using, let's say, 30 dBm transmit power or using 10 dBm transmit power, the current consumption requirements are altogether different. You'd see current consumption of 125 milliamps when using 30 dBm and a current consumption of 30 milliamps when using 10 dBm. So if you're sending 10 uplinks a day, this is the amount of charge that you're going to consume. And that's a really drastic difference, which basically can be summarized that with high transmission power, you can reach extremely long ranges, that's true. But since you suck in more current, you drain battery in no time. So you have to be very cognizant about the latency profile, the classes, because they impact battery, but also be very cognizant about the transmit power. You have to understand that higher the transmit power, longer the range, you'll be really happy. But then at the same time, you'd become really sad really quickly because the devices will see batteries being drained in just no time. So you have to be very careful on what transmit power you're using based on what your range requirements are and what your battery life requirements are. But then one thing that you have to note is that you can't always send messages on really high transmit powers. You can't. You can't use 25 dBm on devices because these are regional restrictions. So my country, for example, where I'm from, India, India has a certain EIRP limit or a transmit power limit above which my devices cannot send information. or European region, for example, has a transmit power restriction or AIP restriction of 14 dBm. So these restrictions are regional based, and you have to understand them before we really choose the radio. And there are more regional parameters. In order to understand them, just try to understand spectrum once. So the entire wireless communication runs from a few kilohertz to a few gigahertz, right? The initial FMs running on 80 kilohertz and those range, but with millimeter wave communication technology, you'll see gigahertz as carriers. So this is the entire range of spectrum that we see. The licensed communication technologies, these are 3G, 4G, 5G communication technologies. They work in fixed bands. These are paid bands. For example, GSM works from 2300 to 2310 megahertz. These are the bands that the telcos have purchased in order to operate their 3G, 4G networks. But where LoRaWAN essentially works is in the unlicensed spectrum. And the unlicensed spectrum in India varies from 865 to 867 megahertz. There is a recent increase in the megahertz from 868, but just for the sake of simplicity, 865 to 867 megahertz for LoRaWAN. Now, that is not constant across the globe. By that, I mean the European region will see a different licensed spectrum, unlicensed spectrum. The US might see a different, Australia might see a different one. So every country has defined their own ISM band, which is industrial, scientific, and medical band. This is the unlicensed spectrum. And you have to only operate your LoRaWAN devices within that band. If you're not, then you're basically doing some things that are practically illegal, and you don't want to do that. So you'd have to buy radios that have the right EIRP or transmit power limits and are actually working in the right band. Because if you're not buying those devices, you're basically breaking the law. But how would I know where my regional parameters are, where my ISM band is going to be really tough? So actually, it's the LoRa Alliance that has done all the heavy lifting for you. It's the regional parameter work group and the regulatory work group that work in conjunction to make this really exhaustive list of all the countries with their unlicensed spectrum listed alongside that you can really quickly, readily use, and you don't have to waste your time. And then you can find out your country within that. You can find this document online, LoRaWAN regional parameters, and you can just quickly understand what your regional band is and then convey this information to your vendor. So that vendor only delivers you the product that is of your band. Now, when your product is of your band, it behaves not just in accordance to the law, but also optimally. We have seen vendors that are really good at making devices of a certain specific band, but can't make good devices for our band. So it's important to ask questions to your vendors that have you been making devices for the Indian band? Because if you have not, then basically we don't want to buy devices from you because the many things will change based on which band the device is using, the radio characteristics, the antenna characteristics, and a lot of testing has to go through, which basically takes time. And only vendors that are providing true global connectivity will have devices of all regional parameters, like Tectalic we just mentioned a while back. There's more to it. I mean, this is how basically I would say the regional parameter index looks like. It has Canada, Australia, Korea, India, Russia, and so on and so forth, many other countries alongside listed. There's something called channel plan that you also have to look at the band after the band, and that is within the band, the devices will operate at certain frequencies, right? They will be working on a certain carriers. So between 865 to 867 megahertz, devices will make use of these channels, 865.0625, 865.4025, 865.985, and so on and so forth. These three channels are mandatory, and these channels are listed in the LoRa line specification document. And out of the 8 LoRaWAN channels that the devices can use, when they're sending joint messages, they have to make use of these 3 channels. And you have to make sure that whenever you're buying a device from a vendor, they have the right 3 mandatory joint channels enabled. that are in accordance to the specification. Or otherwise, what will happen is that the devices will not be able to join the network, and you'll basically have a device that just can't join the network because it's not using the right channel frequency. So make sure that when you're having conversation with your vendor, you share your channel plan with them appropriately so that they enable the right channels within it. Otherwise, device will be of no use. Also, make sure that when the devices are received at your premises, they are using bandwidth of 125 kilohertz. By what we mean is that when the devices are using, let's say, carrier of 866.3 megahertz, they'll basically deviate from minus 62.5 to plus 62.5. That's basically the bandwidth, plus minus 62.5. So you have to make sure that devices are using bandwidth of 125 kilohertz and they're sending joint messages, because that is mandatory. You have to make sure that devices are using bandwidth 125 kilohertz and use one of these three channels to send joint messages, or else the devices will not join. Now, there is so much more in radio characteristics, and this is basically one thing that we wanted to pull together for you to see. This is actually real LoRa signal recorded in our real-time spectrum analyzer. You can see the peaks. You can see each channel bandwidth, its carrier, and the spectrum trace of the LoRaWAN uplinks. So this is how the uplinks look like. Now, you have to make sure many things here. You have to first make sure that the right carriers are used. You have to make sure the bandwidth is appropriate. It's 125 kilohertz. And then you'll also have to make sure that the channels are used randomly, as well as whenever the devices send information on a certain channel, their power distribution is uniform. It can't be like a device send a good signal on a certain channel, but a really poor signal on another. So these radio characteristics will make or break the device network performance. And unless otherwise taken care of appropriately, you'll start to see degradation in range, in the packet success rate, reliability, downlink performance, and whatnot. Sensors, controllers, radio, they all together play a really crucial role, and these device best practices have to be in mind when choosing the right vendor and right devices. So I'll give you a quick summary of what we just discussed around sensors, controller, and radio. We talked about sensing requirement. We then talked about accuracy requirement, what your range looks like, what's the operating temperature that you're working in, then the zero drift and the sampling rate. There's so much more that we wanted to discuss, but it's kind of hard to put it all together in just one webinar, because we also want to have everybody on the same page. Probably in the next webinar or some one-to-one calls, we can talk in length about everything else that you need to keep in mind to make sure that you make the right choices and don't fail at scale, because it's really impossible to fail in a lab environment when you're actually not going outdoors. That is harsh. But as you scale up, as the number of devices increases, when the real-time environment get harsh, you have to make sure that these best practices are taken care of in the choice of choosing the right vendors in a very early stage of the product, because devices is one part of the whole story. If they're not taken care of, you'll basically see everything falling apart in just no time. Now I believe everybody has this really clear sense of device behavior. By that, I mean that if the devices that you are buying are of two vendors, these devices will share different behaviors. No two devices in the world coming from two vendors will have the exact same characteristic. They might be different in the radio that is being used, the antenna, the controller, the firmware, the downlink settings, sensors, whatever it may be. Two devices just cannot have same specification, right? That also sends a signal. If two devices cannot have the same specifications, two devices just can't have the same performance. Not on the sensor level, not on the performance of the network. If two devices do not share the common specification, they also don't share common performance. And that is something that we are seeing to be really overlooked in the ecosystem today. For example, if you have a gateway and you have a location just 2 kilometers from the gateway, it might happen that device one will have a range, but device two may not, because the radio is different, the EIRP, the radio profile, the antenna characteristics, all of that may be different for two devices. And it can be really possible that at the same spot, at the same distance away from the gateway, one device has coverage, but the other device just does not. And that has happened because, probably the first device has got, certified, has better radio, has higher transmission power output, is made on another band. And that is something that we wanted to point out. And that is what we are trying to point out in almost every discussions that we are doing with our vendors, with our customers, that whenever you're doing surveying, whenever you're trying to understand whether there is a coverage in network or not, you don't rely on the gateway. It's not the gateway that provides the coverage. It's the end devices that get the coverage. So it can happen that gateway has a coverage for one end device, but gateway doesn't have coverage for another. So you have to test the right device to make sure that you have the network presence. Because network presence for one device doesn't necessarily imply that there will be a network presence for the other device. So that is what actually the ecosystem is doing today. We are seeing devices being installed are different from the devices that the testings have been done with. So we are seeing the testings being done with a device that has got GPS. These are certified devices. These are really costly devices coming up from vendors that have been in the universe for quite a while and that have made really good antenna specification, very costly radio specifications, and really right firmware, GPS. Everything is in line for these devices, and you do testing with these devices. You go to different spot and test the entire network coverage with these devices, but the device that you actually deploy in the field are altogether different. They're not the same. They don't share the same specifications. So there's a really high chance that device A will have connectivity in the same spot, but device B will not. But what really matters, what really actually matters is that the device B, your device, has to have coverage in that spot. So you actually want surveying to be done with device that is going to be installed in the field, that is going to be installed in the project, not the device that is all classy, all good in 9 different categories. You want to test network presence of device over here, over there, everywhere you want to have network. So you essentially want surveying to be done with a device which you are developing or you have purchased, not a device which is LoRaWAN certified, has good antenna, has good transmission power. It has to be your device that is to be used in surveying. Now you might ask me, hey man, our device this is actually what you want, right? This is the heat map. You essentially want a heat map that says that this device will see strong signals in these regions and will see weak signals in these regions. So what you essentially want is a survey report in form of a heat map of your device at different spots where you actually want coverage. That's the kind of a heat map that you want out of your device. But what the ecosystem so far is doing these testing with a device that is different altogether. These are more devices that had GPS in them. Now you might ask that how can I generate a heat map out of a device that's got no GPS in it, has no testing firmware, the device itself is not certified, it's in the development stage, or the vendor has not really done the certification yet, or the devices are not so costly, these are low cost hardware, then if I don't have it all, how can I still do the testing? I would say you cannot, of course, because these modes are being used so far by the ecosystem to do the testing. But in reality, the true coverage, the representation of true coverage can only be done with the devices that are going to be installed in the field. Everything else is just false hopes. You can do a testing, get a really nice coverage, and at the end of the day, when your device deploying your devices, find out that there's no coverage at all. So if you can generate a heat map using your device, that will be the true representation of coverage in the proximity. And what if I say that we can do that? And we can do that with our product NetC. So this is the gap that we were identifying ourselves, talking to the clients, working out ourselves, doing testing, doing surveying, eventually realizing that one device provides coverage, but the other doesn't. We made a tool that can enable you to test your devices, do survey with your devices, no matter whether your device is a GPS, firmware, certification, nothing matters. Any device of any vendor can be used for surveying with NetC. And how it will do that is something I can really get into, but it's going to be really technical because we have just patented it and we are in the process of getting the patent grants also. But I just showed you a slide a little while back. A slide was actually from Netsea. So this is how the portal looks like. This is a generated report. You can see I just actually generated it for you on September 19. It is actually a device, which is this tactilic device, which has got no GPS in it, no testing firmware, no application server which actually sees location coordinates and does all these heat mapping. This is an ordinary device that we just took off the shelf and started testing with. How did we do that? With the just help of a Netsea app and Netsea web portal. So I'll give you some stats around Netsea, and you'll be very happy to know about the product that we have launched and benefits around it. One, so far, the way the testing are being done, they are just not precise. You're using devices that will not be installed in the field. So no matter how rigorous your testing efforts are, they're basically not precise. With the next generation LoRaWAN wireless sensor networks that we are going to enable through Netsea, and we have enabled ourselves in India, they'll be giving ultimate precision on surveying. You don't have to instill any further costs other than your own device that you have bought. You don't have to buy external hardware that is so costly, I believe. There's no added cost involved in terms of hardware when you're going to do testing with Netsea. There's no additional firmware. You don't have to worry about making the right firmware, integrating GPS with your device, then making a really nice looking application portal that can show you the lat long information. No, nothing. All you have to do is to sign up on Netsea, get the app, and start the testing with your device, and it will generate a report for you. Some stats are over here. We have used ourselves Netsea since the dawn of Sendra. Since the early days, we have used Netsea, and I must say that it wasn't so good looking in the initial days because we were using it ourselves. But we have used Netsea in over 75 plus cities in India and does have done a really rigorous testing across this beautiful country. So Netsea has been in 75 plus cities. It has actually collected over a 1 million data points because every project that we do, we make sure that we make use of Netsea and the device that the customer has bought from their vendor and do the testing and help them understand, okay, this is the kind of a network coverage presence that we are able to deliver with this network pricing and gateway installation. So since we do that, we do our testing very rigorously. And so far we have done over 1,000 surveys and thus have generated over 1 million data points. And that is the last one and really important. The Netsea has used over 100 devices because we have onboarded so many vendors on our portal so far. Some of them have exclusive partnerships with us, like Tectonic I just mentioned. But there are much more vendors that are out there that we have tested devices for and very clearly showed this to our customers that, see, we have 3 devices from 3 vendors. This device costs the most, this device costs the least, and we are taking these 3 devices on a journey of our Netsea surveying. And we do that and show them the difference in the coverage patterns. We help them understand that even though this device is costlier, you'll be able to get the project up and running with just 2 gateways. But if you're going to make use of this low cost hardware, which is not having the right radio, right antenna, nothing is up to the mark, not certified, you start to see there are patchy coverages, and then you will actually need more gateways to provide coverage with these not so carrier grade devices. So that's why we have ourselves used in our office in different parts of India over 100 devices that are being tested with Netsea by us and by our customers of Netsea. So other than what I just mentioned, the ultimate precision, no cost, no additional firmware, what Netsea also delivers is a comparison, like I just said. It also enables you to do comparison analysis of the performance of 2 end devices or 2 gateways also. It also enables you to do client handover very plain and simple. You will basically do network installation as network operator, do the testing with your client's hardware, and show them very plain and simple that, boss, this is the report of your device's network presence as of today. Now, if you want a dense network presence, then basically we can modify our gateway repositioning and install more gateways to give you better network presence, but with an added cost. But that information exchange is going to be really transparent when you have the testing done with the actual hardware of your customer. It also then enables you to do optimization. It tells you these are the weak spots, these are the good spots, and then you change your gateway positioning to make sure that you can optimize the network presence in a better format. Well, there's one more thing, and that I think probably I should close the webinar today to respect your time, and that is that Netsy outshines blind spots, and that is something that is practically impossible to be done by GPS devices. By that, I mean that not just that the Netsy tells you that this is the point where you have really good signal. These are the points that you have poor signal, but it will also tell you that these are the points where you went, but there was no coverage at all. And as you can, yourself think that if you have a GPS device that you're doing testing with, you go around to different spot, do testing, but you will only get information of where your coverage is and what is the quality of coverage. But it will miss out on all those points where you went, but you didn't find coverage altogether. Because the GPS, whenever it's going to be get connected to the GPS satellite, then process the uplink and send messages. Only when there is a link between the device and the gateway, that location information will be updated on the application server. Otherwise, it's going to be lost. So there's no way you can identify the spots where there is no coverage using the conventional method that's being used by the ecosystem so far. And that is something that only Netsy can deliver. It helps you outshine the blind spots. Now, I can go on and talk about all the other benefits of Netsy, but I can't do that because I also have to respect your time here. But I believe by now you get a really clear understanding of why not to do testing with device of different specification, why to do testing with devices that are going to be installed in the field, and how Netsy will enable you to do that. With that, I'll basically summarize our webinar for the day. I think you all enjoyed it as much as we enjoyed making it. We first understood the device best practices, right? We understood that we have to make sure that devices are top-notch. Next, we understood that devices are composed of three major components: the sensor, the firmware, and the radio. Then we realized that we'll start to work on each individual component and list out all the best practices. And we were able to do that on an abstract layer in this webinar, just to bring everybody on the same page so that they understand what's going on. So that in the next webinar, we can go even deep dive and understand how you can better implement the device best practices to really upscale. Then we found out that, two devices cannot really have the same specification, necessarily implying two devices cannot have the same performance. And you have to make sure that you do testing with the devices that are your devices, not the devices that are costly, certified, have GPS within them. And that's where NATC will transform and make sure that we enable next generation LoRaWAN wireless sensor networks in India and globally. With that, sign off. Thank you all for joining, and I hope you enjoyed. I'll be now looking at all the question and answers and try to answer as many of them as possible. But don't worry if you have a question that you have written and not able to answer it due to the time constraints, we'll definitely reach out to you over email, and our pre-sales team will definitely have a consultancy call with you just to make sure that your requirements are properly listened and we deliver you the right solutions around them so that you can enable the massive IoT dream with LoRaWAN. Thank you.
Hey guys, we'll be starting the Q&A part of the webinar now. If you have any questions, feel free to put in the chat or in the Q&A section, and Manvendra will be happy to answer that.
All right, let's see some questions here. We're seeing so many questions, and I hope everybody actually enjoyed the webinar so far. I have to scroll up to see all the questions. Okay, just 1 second. Um, We operate a very industrial commercial LNS and have a network management system to monitor its third parties with let explains or carrier right about. I think Ronit has already answered that question, but we can probably do this over a call in detail. There's this question around Netsy, is it an open source tool? Well, Netsy is not open source. We are actually commercializing Netsy. So if you'd want to discuss the costings and talk about the details, we will reach out to you because we already have your email IDs, and then we can have a demo session tailored around your requirements, and then we can discuss the pricing as well. Can you please tell me more? How do you trace monitoring LoRa radio frequency quite accurately? Do you use any SDRs for these? Now, so we have a real-time spectrum analyzer that we use to trace the radio frequencies. We have an anechoic chamber, a complete RF lab setup to do all these measurements. We don't use SDRs per se, but yeah, they can be also used to do the same. Oh, thanks a lot. Somebody said that have some water now. That's so nice of you. Thanks, Saurabh. I think Ronit, who is my subordinate, has probably answered mostly all the questions. So whatever questions that you might still have and we haven't answered, or probably you might, realize you have them later, you can definitely reach out to us on info@sendraco.com. We'll probably share the slide deck with you all just so that you can understand things better and remember them. And if you have any questions, we can discuss them over email and talk about them over a call as well. I think, Ayush, we can close the webinar for now then and say goodbye to all the participants.
Yeah. So, guys, we are putting out our company's email over the chat section. So you can reach out to us with any further questions or any inquiries or queries that you might have. If you can see in your chat box, info@sandraco.com. Please feel free to reach out, and we'll be happy to take any and all queries that you might have. Thank you, guys.